Welcome to the deep dive. If you're an AI researcher, or maybe an ML engineer trying to keep up with LLM reasoning, well, this is for you. We're looking beyond just, brute force chain of thought today.
Yeah, we're diving into some foundational research that really tries to shift how models tackle complex problems.
Specifically,
We're looking at a paper called RLAD, Training LLMs to Discover Abstractions for Solving Reasoning Problems.
yeah.
It proposes a pretty novel two-player reinforcement learning approach.
Okay, two-player RL. Sounds interesting.
It really is. It's about teaching models not just to find an answer, but to actually plan how they're going to find it.
All right, let's get the key summary down first. For anyone needing the quick version, what's the core idea here?
Okay, so the main issue RLAD tackles is that standard RL post-training, well, it often makes LLMs focus on solution depth,
Meaning,
really long, sometimes kind of rambling chains of thought.
yeah,
The paper calls it degenerate exploration. Basically, the model isn't good at capturing or reusing effective strategies.
right. It just keeps talking, hoping it stumbles on the answer.
Pretty much. So the solution RLAD proposes is this concept of reasoning abstractions.
Abstractions, what are those exactly?
Think of them as concise natural language hints. They capture procedural knowledge, like how to do something or maybe a key fact, acting as high-level sub-goals or meta-strategies.
Okay, like a little strategy note. And how does RLAD make this happen?
Through this two-player RL game, it trains two policies together. An abstraction generator, call it PIOPS, and an abstraction conditions solution generator. They cooperate.
Got it. Planner and executor. And the big result, why should we care?
Performance and efficiency. RLAD significantly beat standard long-code TRL methods like DAPIO, showing around a 44% average improvement on the AME 2025 benchmark in their tests.
44% is substantial.
It is. And crucially, they found that if you have a fixed compute budget at test time, spending some of it generating diverse abstractions gives you way more bang for your buck than just sampling more and more solutions using the same old strategy.
So planning pays off more than just brute force solving.
That's the key takeaway. Strategy over just sheer volume.
Okay, let's unpack that problem statement a bit more. Why does standard RL lead to this degenerate exploration? You'd think rewarding success would lead to better strategies.
It seems intuitive, but the issue is how the reward works. Usually it's just a simple 0 or 1, did you get the final answer right?
Right, pass-fail.
So the model figures out, hey, if I just generate a longer trace, more steps, more words, maybe I'll accidentally hit the right combination. It optimizes for depth or volume.
I see. It's gaming the reward signal.
Kind of, but what we actually need is breadth exploring different ways to approach the problem. We want the model to think strategically, not just iteratively.
So instead of just adding another calculation step, we want it to pause and ask, is this entire approach working? Should I try, say, using modular arithmetic differently?
Exactly that. And RLAD forces this by making the model propose a strategy, the reasoning abstraction, before it dives into the solution steps.
In these abstractions, they're like compressed know-how.
Yeah, they can represent shared procedures like apply algorithm X or key facts like remember lemma Y. They act as high-level guides or, priors for the solver.
The paper had that math example, right? The congruence one.
P plus P1 equiv 25 P mod 1 sic. A standard QT might just flounder around with algebraic manipulations.
And get lost.
Right. But a good abstraction from P-pleiabs might say, hey, try using the quadratic formula, but in modular arithmetic. Or maybe a warning. Hold on, check if PI even has a multiplicative inverse modulo 143 before you use pval day.
That makes sense. It's like having a map versus just wandering. Did they prove models need training for this?
They did. They showed that good abstractions, maybe written by humans or a stronger model like GPT-4, do help a capable solver model. But crucially, that solver model couldn't come up with those useful abstractions by itself.
So the ability to both generate and use good strategies doesn't just emerge automatically. You need to explicitly train for it.
That's the core motivation for the RLAD framework.
Okay, this brings us to the really neat part. The two-player RLAD game. We've got the planner, proposing the abstractions of you all for a problem 6-dol.
Correct.
And the solver, LAOL, generates the actual solution steps using both the problem 6-dollars and that abstraction Zabiel.
Exact.
But how do you make sure a playol actually uses Zabiel? Couldn't Smart Solver just ignore the hint if it thinks it knows better?
Yes. That was the key challenge they tackled. It's an asymmetry problem. Let's break down the rewards first. KXL, the solver, gets a simple reward. 1 if the final answer is correct, A0 otherwise. Standard stuff.
Okay. And the planner, how does it get rewarded?
Its reward is based on the expected success of the solver when using its abstraction. So T-sol, C-sol. If the abstraction that PALS proposed makes E-sol more likely to succeed, PF-sol gets a higher reward.
So they're incentivized to cooperate. Kias wants to give useful hints, and ALS uses those hints to get the answer right.
That's the idea. But you hit on the problem. What if PL is already quite strong? It might learn to just ignore Symbol, especially if PL isn't generating great hints yet. Or, conversely, PLs might just link the answer in a hint.
Right. How do they fix that?
This is the clever part, the fix in equation 3. They train PLs on a mix of inputs. Sometimes it gets the problem 6Cs and the abstraction solved. Other times, it just gets the problem 6L with no abstraction, so goes as empty.
Okay, so it sees both scenarios.
Yes, but here's the kicker. They deliberately zero out the reward for any solution that was generated without an abstraction. Tilly said.
Wait, even if the solution was correct?
Even if it was correct. If PL solves the problem on its own, without using a hint from PLs, it gets absolutely no reward for it in the training calculation.
Wow. Okay, so it has to learn to use the abstraction to get any positive feedback.
Precisely. It's a strong signal. It forces the PL to become dependent on PLs for optimizing its own reward. It learns that the only way to win the training game is to utilize the hints provided.
That's a really elegant way to enforce that dependency. Did they mention other practical things needed to make this training work?
Definitely. Initialization matters. They found it helpful to warm start PABs using supervised fine-tuning, SFT, on abstractions generated by stronger models first. Get it off to a good start.
Makes sense. Give the planner some initial idea of what a good plan looks like.
Right. And they also highlighted the benefit of curriculum training, starting with easier reasoning problems and gradually increasing the difficulty. This helps prevent the RL training from collapsing early on, which can happen with complex reasoning tasks.
So careful initialization and gradually increasing difficulty. Standard RL good practices, but crucial here.
And that combination of including the no abstraction prompts, but masking the reward for them, was key to preventing the solver from just learning to ignore the planner.
All right, so all this careful engineering, what did it actually achieve? Let's talk performance. How did RLAD stack up against the baselines like DAO?
The results are pretty impressive, especially considering they used a relatively small 1.7 billion parameter model, Qwen 3 1.7b, as the base. Looking at Table 2 in the paper, RLAD consistently outperformed both the base model and DPay across several math benchmarks.
Like which ones?
AME 2025, Deep Scalar Hard, AMC 2023. These are known to be quite challenging reasoning datasets.
And the headline number you mentioned earlier, the AME improvement.
Yeah, on AME 2025, the DPO baseline got around 37.9% accuracy. RLE, just by taking the best solution generated from 4 different proposed abstractions, hit 48.3%.
That's over a 10 percentage point absolute gain.
Exactly, which translates to that roughly 44% average improvement over DPO they reported. It really suggests that teaching this planning capability is a significant step up from just rewarding longer reasoning traces.
What really jumped out at me, though, was the generalization finding. You mentioned RLAD helps even when you don't give it an abstraction at test time.
Yes, that's the WOAB setting they tested. Even when they just ran the trained PIL model directly on the problem without providing any abstraction hint, it still performed better than the baseline models trained without RLAD.
So the training process itself made the underlying solver model fundamentally better at reasoning. It wasn't just learning to follow instructions.
That seems to be the implication. The process of being exposed to and forced to utilize diverse, high-level strategies seems to improve its general reasoning machinery. It suggests it's learning more robust underlying procedures, not just pattern matching for specific hints.
That's fascinating. Okay, this leads us to maybe the most practical finding for people running these models, the compute trade-off, this idea of depth versus breadth.
Right. This is about how you best spend your compute budget at inference time. Do you sample more solutions from the same strategy, or do you sample more strategies first?
Depth being more solutions, breadth being more abstractions.
Exactly. The intuition is pretty straightforward. If your model is stuck on a fundamentally flawed approach to a problem, generating 10 more solutions using that same flawed logic probably won't help much.
You need a different angle.
You need a different angle, a new strategy. And that's what sampling a new abstraction provides. Their quantitative results, especially in Figure 5, back this up strongly.
How did they show that?
They show that as your total compute budget increases, allocating more of that budget towards generating abstractions first, that's the MM parameter, gives you better performance gains than just increasing the number of solutions you sample per abstraction, the K parameter.
And they had that Kettle and all normalization. What was that about?
Ah, right. Kettle helps control for tiny gains you might get just from resampling solutions, like maybe the model fixes a small calculation error on the second try. By setting a Delaroy threshold, they're focusing on gains that come from a real strategic shift, the kind induced by a different abstraction, not just minor refinements.
I see. It isolates the impact of the strategy itself.
Precisely. And Table 3 drives it home. Under a fixed total compute budget, say n-totter 2 samples, doing known dollar abstractions times knowledge solutions per abstraction consistently beats doing one abstraction, or none, times 2 toller 2 solutions.
So, for efficiency, exploring different strategies via abstractions is the way to scale.
That's the clear message, breadth over depth, especially as compute scales.
Okay, we know RLAD works and it's efficient. But what about the abstractions themselves? Are they actually, diverse? And does the solver model really follow them?
Good questions. They dug into this as well. First, adherence. Does actually pay attention to the specific abstractions it's given.
Yeah, does the reward trick actually work in practice?
It seems so. They measured an adherence rate. The trained solver model followed the specific abstraction it was conditioned on about 43.3% of the time. That was significantly higher than if they fed it a randomly chosen abstraction from the pool or one retrieved based on similarity. Those were closer to 20%.
Okay, so conditioning works. It makes the solver more likely to use that specific hit.
Correct. It confirms the training successfully linked the planner's output to the solver's behavior.
And diversity. Are different abstractions leading to genuinely different ways of solving the problem?
They checked this using Semantic Similarity. They looked at the final solutions generated. When the solver was conditioned on different abstractions proposed by PIM, the resulting solutions were measurably less similar to each other. Think an average cosine similarity score of about 0.82.
Less similar than what?
Less similar than solutions generated multiple times using the same abstraction, which scored 0.86 similarity, or solutions generated with no abstraction guidance at all, 0.85 similarity.
So that gap, 0.82 versus 0.85 or 0.86, while seemingly small numerically, indicates that different abstractions are pushing the solver down noticeably different paths.
Exactly. In high-dimensional embedding space, that difference reflects a real divergence in the solution strategy being employed. The abstractions aren't just minor variations, they guide the model towards distinct approaches.
That's compelling proof. Did they look at what kinds of strategies the abstractions represented?
They did a qualitative analysis, yeah. They found the discovered abstractions tended to fall into 4 rough categories.
Okay, what were they?
There were caution alerts, basically warnings like, don't forget to check this condition or avoid this common mistake.
Useful.
Then productive launch points. These gave strategic framings, like reformulate the problem this way or start by considering this case.
Setting the direction.
Right. Third, structural shortcuts, which involved more conceptual leaps, like identifying an invariant or a way to collapse steps.
The clever insights.
Sort of. And finally, blind follow trajectories. These were more like reliable step-by-step recipes or algorithms that could be applied repeatedly.
Interesting. Did the training favor certain types?
They noted that after RLAD training, there was a noticeable increase in the proportion of these blind follow trajectories.
What does that suggest?
It suggests the RL training is particularly good at discovering and locking down reliable, reusable procedures algorithms that consistently work for certain types of problems. It's learning effective, repeatable recipes. So wrapping this up, the big picture here is that reasoning abstractions offer a really valuable, kind of orthogonal way to improve LLM reasoning performance, especially when you have more compute available at test time.
Orthogonal to just making the chain of thought longer or sampling more solutions?
Exactly. It adds this layer of strategic planning that helps the model avoid getting stuck in those deep but unproductive reasoning paths.
What do you see as the main open questions or next steps coming out of this work?
Well, there are a couple of big ones they mention. First, the technical hurdle of getting a single model to be good at both proposing and using abstractions effectively within this RL framework. Their attempts found that the model tended to lose its ability to propose good abstractions during the RL phase when trying to do both.
So maybe it needs a more specialized architecture, 2 distinct parts.
Potentially, or at least a different training approach.
Yeah.
It's an open challenge. The second big question, maybe the more fundamental one, is really understanding why the model gets better, even when no abstraction is provided at inference, that generalization gain.
Right. What exactly is changing in the model's internal workings?
We don't fully know. It hints that the training is encoding something deeper about problem-solving strategies, not just instruction following. Understanding that mechanism is key.
Hey, that leads nicely into a final thought for you, our listeners. If this abstraction generator, EPIAPS, is basically learning to be a high-level planner, is generating a textual abstraction just a necessary intermediate step for training? Could future architectures skip the text prompt entirely?
That's the provocative question.
Could you imagine integrating a latent planning module trained by something like PIABS directly into the model's forward pass, moving beyond text-based hints to internal strategic routing?
It's a fascinating direction. Would it be more efficient, more robust? That's definitely something to think about as you work on building the next generation of reasoning models.